Now, in our last lecture we have derived the partition method to find the inverse of a matrix. We have also shown the need to have such a method in order to tackle the large matrices. We have partitioned a given matrix into some suitable form for us as some B, C, D, E. We have shown that the inverse of this matrix A can be obtained by finding the two inverses of lower order matrices, where we have taken B as a R into R matrix and E we have taken as an S into S matrix. Now, by finding the inverse two inverses, one of R into R and another of S into S, we can find the inverse of the matrix A. Of course, we will have to do little bit more of matrix multiplications also in order to produce the final result. However, there is substantial saving in the total computation cost. Now, let us illustrate this through an example. So, let us take this as an example. Now, let us say find the inverse of the matrix. Let us just take a 3 by 3 matrix, so that it is easy for us to illustrate this. Using partition method. Using partition method. Now, that means we are let us partition it using it this partition. Therefore, we are partitioning it as B is equal to 1 1 4 3. C is the column vector, in this case 1 minus 1. D is the row vector 3 and 5. D is this row vector, and E is a 1 into 1 matrix, that is simply 3. So, this is E, that is 1 into 1 matrix. Now, in order to find the inverse by the partition method, let us also partition A inverse also as we have partitioned this at x, y, z and v. We partition it as this particular thing. To start with the procedure, we need the inverse of B. So, let us start with the inverse of B. So, I need B inverse. So, let us find the inverse of this matrix 1 1 4 3 inverse. So, let us do it straight away. Its determinant is minus 1. So, I will have a minus 1. So, I will have the element 3 here, I have element 1 here and its cofactors and transpose of it. So, I have the inverse simply of B as this. Now, the next matrix multiplication I need, I will pick up from what we have done last time. I need E minus D B inverse C. I need this quantity to determine the next inverse. This is 3 and we have B inverse with a negative sign. So, we can put a positive sign here, and D is this row vector 3 comma 5. So, let us write down 3 comma 5 as your row vector. B inverse is here, that is 3 minus 1 minus 4 1. We have absorbed this minus sign here already, and then we are multiplying by C, and C is this column vector 1 minus 1. So, this is your 1 minus 1. So, let us multiply it out, that is 3 plus 3 5. Now, I multiply this matrix and the vector, that is 3 plus 1 4 minus 4 minus 1 minus 5, and that is 3 plus this is 3 12 minus 25. So, that is 15 minus 25, that is equal to minus 10. Then we have shown that this partition part V, this matrix is equal to, here it is a 1 into 1 matrix, therefore it is an element simply, that is equal to E minus d B inverse C, inverse of this previous part. So, here it is a number, therefore, we simply get 1 upon minus 1 upon 10. Then we have shown that y is equal to minus B inverse C of V. Now, let us substitute B inverse here. So, we can remove this minus sign as plus sign. So, I will make this as 3 minus 1 minus 4 1, and C is the vector that we have here 1 minus 1 into V, V is this minus 1 by 10. Therefore, this is minus 1 upon 10, and this is 3 plus 1 4, that is minus 4 minus 1, that is minus 5, minus 5. Y is also now determined. Then we have shown that Z is equal to minus V d B inverse. Now, V is minus 1 by 10. So, I can absorb this 1 upon 10. D is the row vector 3 and 5, we have used it here, D here, D is here, and B inverse 3 minus 1 minus 4 1. Now, we have a minus sign. So, let us put one more minus sign over here. So, that this is minus 1 upon 10, this is 9 minus 20, that is minus 11, minus 5 minus 3 plus 5, that is equal to 2. Oh, it is a row. Okay, let me write it again. This is minus 1 upon 10, this is minus 11, 2. So, this Z is a row vector minus 1 by 10, minus 11 and 2. Now, the last quantity to be determined is x. So, the quantity x is the vector x is equal to B inverse of I minus C Z. This is the matrix X matrix. Now, let us again substitute B, that is minus 3 minus 1 minus 4 1, and put this in a bracket. I is 1 0 0 1 minus C, C is 1 minus 1 minus 1, and Z we have just now computed, that is let us make this as a plus sign. So, that we have 1 by 10 minus 11 2 minus 11 2. Now, let us write one more step here, that is 3 minus 1 minus 4 1 1 0 0 1 plus 1 by 10. This is a 2 into 1 and 1 into 2. So, it is a 2 into 2 matrix. So, this is minus 11 2 11 minus 2. Now, I can simplify this one more step before I multiply it. 3 minus 1 minus 4 1. This is 1, I can put it here 1 minus, this is 11 by 10. So, I will have here minus 1 by 10. Then I have here this is 2 by 10, let us retain it as 2 by 10. This is 1, that is 11 by 10, that is 1 minus 2 by 10. And sorry, this is the last vector is 1 minus 2 by 10, this is 1 minus 2 by 10, therefore, this is 8 by 10, this is 8 by 10. Now, I can let us multiply it out, minus sign here, this is minus 3 by 10 minus 11 by 10. So, this is minus 14 by 10. Then we have 3 into 2 6 by 10 plus 8 by 10. So, I have we have a this is this is plus 8 by 10, that is what I was looking at, this is plus 8 by 10. So, this will be minus 8 by 10, that is minus 2 by 10. Then this product is, we have 4 by 10 plus 11 by 10. So, we will have 15 by 10, and lastly we have this product, that is minus 8 by 10 plus 8 by 10. So, I have a 0 over here. Now, we have found out all these 4 quantities, we place them in the proper order x, y, z and v, that will give us the inverse. Therefore, the inverse of the matrix is therefore, so A inverse is equal to x, y, z, v, and that is your let us take minus sign inside, 14 by 10, that is 1.4, this is 0.2, this is 1.50 with a negative sign, I am putting minus sign inside. So, I will have this as 1.50, and this was your partition that we had got here, and y is here, that is minus 1 by 10 into 4 by 5, therefore, this will give you minus 0.4 and this is plus 0.5. Then z is here, that is, let us take it inside. So, we will have plus 1.1 minus 0.2, this is 11 by 10 and 2 by 10, minus 2 by 10, and finally, the corner element is our v minus 1 by 10. So, this is your minus 0.1. So, therefore, this is the final inverse of the given matrix, and even though for the hand computation this looks little lengthy, however, in actual computation is much faster, because the amount we are only finding the inverses of 2 matrices of these orders and then remaining are matrix multiplications. This is how the partition method can be applied, which is a direct method. We can apply it for a finding the inverse of a very large system by reducing it into smaller systems. Now, we have mentioned earlier that all the direct methods we can definitely find an operational count, what is the total amount of operations that we are performing, so that you would be able to tell exactly how much computer time that will take if you are using a particular computer, because we know the time that will take for a multiplication and division and the time it takes for addition and subtraction. When once you know the number of addition subtractions and the number of multiplications division that my method has got it, we will exactly be able to say if given a method a 100 by 100 matrix or a 50 by 50 matrix, you would say that this much compute time would be required for us to solve this particular problem. So, let us illustrate it for one of the methods that we have done, the other methods can be done easily. So, let us take the Gauss elimination and perform what is the operational count for Gauss elimination. So, let us take the Gauss elimination and do the operational count. We shall call this as operational count. Just let us remember what we have done the Gauss elimination. We have the system of equation Ax is equal to b, then we have written the augmented matrix AB, we have written the augmented matrix AB. So, let us write it A11, A12, let me take A13, A1n, A21, A22, A23, A2n, A31, A32, A33, A3n, AN1, AN2, AN3, ANN, and the right hand side vector B1, B2, B3, Bn. Now, the method that we have given for the Gauss elimination was, we said take the first pivot, divide by the first pivot throughout, so that we can produce a 1 here. Then we eliminate all these elements below. Therefore, let us first start with the divisions which are less. So, let us take what is the number of divisions let us count them separately. Number of divisions. Now, let us take the first step. Now, in the first step I have to take I have taken the first pivot and divided all these elements. So, the first equation requires division of these n minus 1 elements plus 1 element. So, total of n elements we need for division in the first step. So, let us write as first equation. First equation we need n of them. Now, the remaining part does not have any division. So, let us proceed on. So, let us go to the second step. In the second step is that we take this pivot, this second pivot, use this pivot to eliminate all the remaining elements. So, to do that we are dividing by this pivot all the remaining elements in this row. So, I am dividing these n minus 2 elements plus 1 element, n minus 1 elements in the second step. So, this will be our second equation. There are n minus 1 divisions in the second step. Now, you can see that when we go to the third step, I am now with the pivot at this location. Therefore, I am now using this pivot to eliminate all of them. So, I am now dividing this n minus 3 plus 1, that is n minus 2 elements, and so on. So, let us go on and do it, and let us take the nth step, that is your nth equation. Now, when we have reached the nth step, we have reached this location of this pivot. Now, this pivot divides this to produce the starting the solution. So, it has got one division in the nth step, that gives you the last value of x and the value of this one. Now, I can let us write this as total. Total is 1 plus 2 plus 3 plus so on n. So, that is your summation of n. 1 plus 2 plus 3 so on n. So, this is summation of n, that is equal to n into n plus 1 by 2. Now, the divisions have all been carried out, all the pivots have been brought as 1. So, when we back substitute, there are no further divisions, because the elements have already been made 1. So, there are no divisions, further division. Therefore, the total number of divisions in our Gauss elimination is only n into n plus 1 by 2. Now, let us go to there are two ways we have given. One was to divide by a11 and multiply it. Alternatively, we have given a procedure that you take the pivot, divide by the pivot first that equation, so that the diagonal element becomes 1. So, in this procedure I divided by a11 throughout. Now, the pivot has become 1. Now, the second pivot, now these are all zeros, second pivot is now used and we divide throughout this equation. So, the second pivot has become 1.
If we divide by a11 throughout, it will be n plus 1 terms, n plus 1 divisions.
We do not divide a11 by a11, right. So, when we divide by a1 by a11, we know that it is going to be 1. We are not going to divide a1 by a11, thereby we introduce an error in the round of error. So, we assume that you are dividing this element by this element, it will be 1. So, therefore, the count will be leaving that particular pivot, you need to do it. So, now we need to do the number of multiplications. So, let us find out what is the number of multiplications. Now, let us write down the number of multiplications. Now, let us go back to the first step. So, let me write down as first step. Now, when we have divided by a11, so I have the elements. Now, what we are doing, producing 0, I am multiplying by a21, subtract all the elements. So, what I am doing is I am multiplying whatever the quantity by a21 and subtracting, multiply a21 subtract multiply by a21. So, I am now multiplying n minus 1 in plus 1, that is n times I am multiplying in the first step. So, in the first step for updating the second equation, we are updating the second equation, and that requires total of n multiplications. multiply, subtract, multiply, subtract and so on. Similarly, for updating the, now the first step requires that this element be made 0, this element be made 0, all of them. So, updating the third equation, I am now multiplying by A31 and subtract A31 and subtract A31 into this and subtract. Therefore, I am still continuing with n multiplications and so on. For the nth equation, updating the nth equation, I need n of them. A total number of equations updated are second to n. There are n minus 1 equations that are updated. Therefore, the total at this for the first step is n into n minus 1. There are n minus 1 equations that are updated starting from second to n. Therefore, n minus 1 into n will be the total multiplication that will be required. Now, let us go to second step. Let us go to second step. Now, when we are at the second step, we are now updating the third equation onwards. So, we are now updating the third equation. Now, let us look at this one. I am using this pivot here. I am multiplying this by the by this A32 and subtract, multiply this quantity by A32 and subtract, multiply the quantity here by A32 and subtract. So, I have got here n minus 2 plus 1, that is equal to n minus 1 elements are updated. So, I have now updating n minus 1 elements now, 1 less than in the previous case. So, similarly, I am updating the fourth equation, the same number. So, finally, updating the nth equation, I have n minus 1. Now, the total equations that are updated are from third to nth, therefore, n minus 2 updates are there, therefore, n minus 2 into n minus 1. Therefore, the total here is equal to n minus 1 into n minus 2. Now, we can generalize and then get the total for this, total for the forward elimination. We have eliminated in the forward direction. So, we will write down the total for this, and that will be, we can take this quantity that is we started with, and that will be summation of n into n minus 1. The next one is n minus 1, n minus 2, the next one will be n minus 2, n minus 3 and so on. Therefore, this will be simply summation of n into n minus 1. Let us simplify this, let us open this up. This is summation n square minus summation n. Summation of n square is known to us, that is n into n plus 1 into 2n plus 1 by 6, and summation n is n into n plus 1 by 2. Let us combine them, n into n plus 1 by 6 into 2n plus 1 minus 3. So, this is 2n minus 2. So, I will take out 2 outside. So, I will have n into n plus 1 into n minus 1 divided by 3. So, the total I require for forward elimination is this many of them multiplications. Now, we have completed the forward elimination. So, the back substitution is now to be taken care of. Let us now take what will be the back substitution. Now, let us just have a look at this one. When we have completed the procedure, what we have here is the upper triangular matrix. So, the let us write down what it is going to look like. It is going to be an element like this, one element like this, so on. I have an 1 here. We are divided by the pivot. So, we are having 1 1 here and we have got elements over here. This is how the matrix is going to look like after we have completed this elimination in the forward direction. Now, the nth equation does not have any multiplication because this is equal to this as the solution. Therefore, nth equation there is no multiplication. There is no multiplication in the nth equation, just this x n is equal to the right hand side whatever the element. So, there is nothing computation involved in the last equation. Now, let us go back to the n minus 1th equation. Now, look at this n minus 1th equation. This is containing 1 here, element here, element here. So, I am now substituting this value that we obtained x n here, multiplying, taking to the right hand side, or take to the right hand side and multiply. So, I have a multiplication here to be done with this particular element and a subtraction. So, I have n minus 1th equation, I have one multiplication to be done. Now, go to the n minus 2th equation. The n minus 2th equation is looking like 1 element, element, element here. Now, the solution of x n minus 1 and x n were determined. Therefore, I am multiplying this, taking to the right hand side and subtracting. So, I have got two multiplications that are to be done here. So, I have two multiplications to be done here, and so on. I go to the first equation. Now, let us look at the first equation. First equation, I have to multiply these n minus 1 elements, take to the right hand side and add them. Therefore, I have got n minus 1 multiplications to be done here. So, this requires n minus 1 multiplications. Therefore, total for back substitution, let us do it. Total for back substitution is summation of n minus 1, summation of n minus 1. So, that this is n minus 1 into n by 2. Now, we have completed the count. So, let us now write down the total multiplications now. The total multiplications here, that is the total for forward elimination plus total for back substitution. So, I will have here n into n plus 1, n into n plus 1, n minus 1 by 3 plus n minus 1 into n by 2. So, this will be the total multiplications in our Gauss elimination procedure. Now, let us simplify this. I will take this quantity here. So, let us take out 6 outside, n into n minus 1 outside. So, that I have here 2 times n plus 2, I have taken n into n minus 1 by 6. So, I will have 2 n plus 2 plus 3, that comes from 3. This is 1 by 6 n into n minus 1 into 2 n plus 5. Therefore, the total count of the major operations, normally operational count would imply the total number of multiplications and divisions. The reason being that the time that is taken for subtraction or addition is much smaller factor compared to the multiplication and division. So, let us take what is the total multiplication and the divisions. And that is total divisions, we have n into n plus 1 by 2 plus 1 by 6 n into n minus 1 into 2n plus 5. So, this is our total multiplications and divisions. Let us simplify this. This is I can take n by 6 common. So, that will become 3n plus 3 plus n by 6 I have taken, let us multiply it out. This is 2n square plus 5n minus 2n minus 5. So, that is n by 6, that is equal to 2n square yes 6n minus 2, and we can remove a 2 from here and write this as n by 3 n square plus 3n minus 1. This is the exact number of multiplications and divisions that Gauss elimination has got. Therefore, we normally say for large n Gauss elimination is of order of n cubed by 3, or simply we write down as n cubed by 3. Now, the reason why it is so is obvious, because n square is much smaller compared to n cubed when n is large. For example, n is say 100. So, this what we are talking of is 100 cubed compared to 100 square. So, this gives you 10 to the power of 4, this is 10 to the power of 6. So, this is a much smaller compared to this one. Therefore, for very large n we usually say that the number of operations for Gauss elimination is of the order of n cubed by 3. However, we can give the exact number of total multiplication and divisions that are required. As I said, this is usually called the operational count. First of all, this is called the operational count. Yes.
So, can we denote multiplication and division both the same quantity and
The actually the time that is taken for the on any computer for division and multiplication is same, and also the time that is taken for addition and subtraction is identically same, but the time that is taken for addition subtraction is a much factor less than the time that is taken for multiplication. That is why the multiplications or division always taken together and addition subtractions are always taken together. Now, we can count very easily the total additions and subtractions, and that is, if you just look at the, let me write down this slide. Let us leave the divisions, let us start with our multiplications. With every multiplication we are doing, there is an addition or subtraction involved. Let us go to the first step. I am now multiplied, subtracted, there is a subtraction, multiply, subtract, multiply, subtract, multiply, subtract. Therefore, if you look at the first step, the number of additions subtractions are identically same as the number of multiplications that we have, because for each multiplication we have this. So, all these steps we require it. Now, you go to the second step, it is identically the same story. The second pivot, now we have multiplied this by the 3832 subtracting, again we have one subtraction. With this multiplication I have a subtraction, with this multiplication I have subtraction. Therefore, the entire the Gauss elimination procedure, the forward one that we have gone through has got all of them identically same addition subtraction. Now, let us go to back substitution. If I go to the back substitution, this last element has no subtraction, because this is equal to this. Now, the n minus 1th equation I have multiplied, taken to the right hand side, then subtracting. Therefore, with this multiplication is attached one subtraction. So, n minus 1th equation 1 subtraction. If I go to the previous equation, I have multiplication here, there is a addition here, goes to the right hand side, there is an addition there. Therefore, along with the two multiplications I have got again two addition subtraction. Therefore, the same thing if you go to the first equation, there are n minus 1 multiplications here and n minus 2 additions here and one addition to the right hand side. So, n minus 1 additions. Therefore, along with each multiplication we have one addition associated with it, and hence the operational count for the addition and subtractions will be the total multiplications that we have, the grand total multiplications that we have, that is your the here we have got this part. This is your total divisions and this is your total multiplications and divisions. Therefore, this part will be our total addition subtractions in our operational count. Therefore, we will have total additions or subtractions will be 1 by 6 n into n minus 1 into 2n plus 5. Now, with this you would now be able to say how much exactly a particular problem is going to take time, because I know the number of addition subtractions, I know the time that is taken for each addition subtraction, I know the time for this major operation. So, I can just multiply the total number and give the exactly what is the computed time that it will take when once you know the clock speed or the CPU speed, when once you know the CPU speed and the times taken for this, you can immediately count it and then say this is going to take this many seconds of time or this many minutes of time for this particular problem. So, this is the advantage of the direct method, that we shall be able to give the exact time that will be taken for a particular problem. Now, we can do the same analysis for the other methods also. I will leave this an exercise, but give you the solution for this. So, for large n, the Gauss-Jordan procedure approximately takes, you remember when the Gauss-Jordan procedure was, when we are making the these eliminations at any pivot, later pivot, we are eliminate, if I take the second pivot, we are doing elimination below and elimination above. So, when I go to this element, I am now eliminating below as well as above. So, I now need to add to this what is the thing that is going to take for this making this upper triangular part also as 0. Therefore, that involves, and we mentioned when we have solved an example, we said that Gauss-Jordan is much more expensive than the Gauss elimination procedure. However, we shall use it for finding the inverse of a matrix, which is very convenient procedure, and the number of operations is n cubed by 2. These are the again the major operations. That is your multiplications and divisions. Therefore, it is n cubed by 2, whereas Gauss elimination is n cubed by 3. Then LU decomposition is identically same as the Gauss elimination procedure. So, this also takes n cubed by 3 major operations. The other method that we have given is the Cholesky method, that is the LL transpose decomposition, which we called it as Cholesky method. Now, here we would like to take advantage of the symmetry of the matrix, that is even in the computations as well as in the storage. Normally, when we do the storage for Cholesky, we store only either the upper triangular part or the lower triangular part and do the operations, and the operations, that is n cubed by 6, that is almost half of the Gauss elimination procedure, which should be expected. Now, I can give you the exact number for this. This is 1 by 6 of n cubed plus 9 n squared plus 2 n. This is the number of operations. Now, very often when you are solving the ordinary differential equations or partial differential equations by the finite difference or finite methods, we come across tridiagonal system of equations. This is a very important system of equations that arise in the practical applications. What is that system? Is that your A is going to have only 3 diagonals, that is your x is equal to p. So, this we shall call this as a tridiagonal system of equations. It is a tridiagonal system. Now, interestingly, equation, the number of operations for this tridiagonal system is 5n minus 4. That means, if I am solving a 100 by 100 system tridiagonal system, it is going to take only 500 minus 4, that is your 496 major operations, nothing more than that. That means, it is going to be a few milliseconds. This is how the system that I talked originally, that in a practical problem you come across millions of equations. The millions of equations, when you are solving it, when you are solving that system of partial differential equations or system of ordinary differential equations, when it produces that, you use the method in such a way that you produce simplest system possible, say a tridiagonal system, or I have a 5 diagonal system, something like that. Now, when once you have such systems, we can have that the number of operations is enormously less, and hence we will be able to solve even millions of equations within a very short span of time. It may, if you are taking few million, hardly it may take few hours on this. So, but still the problem can be solved. So, that is the reason why I say that the suitable method should be used for solving any particular problem, be it a differential equation or any other problem. However, if it is not possible for us to put it in this form, where it is possible for us to write in this, use these methods in this particular format, there is no alternative for us to go for the iterative methods. Now, if you have a system of equations of the order of 10 to the power of 6 by 10 to the power of 6, it is almost full, or it has gone a band structure such as bandwidth is very large for the matrix A, it is not possible for us to store this on the computer. All these direct methods require storage of the entire structure into the computer. So, all the elements are stored. Now, since all the elements are stored, you need sufficient space to store the given system of equations, and the later part, that when you are solving them, you also require sufficient space to use that part. If it is not possible, then the only alternative is that we use an iterative method, wherein you can load one equation at a time, or 100 equations or 1000 equations at a time, solve it, then load the next 100 equations or 1000 equations and solve that. Therefore, in such problems where the direct methods are not applicable, that is system is very large and the A is also a little dense, then we would like to use the iterative methods. So, let us define what is iterative methods for the solution of these problems. You see, these methods are very important, because in particular when you have, for example, design an aircraft or design a motor car, the number of variables that are there at any particular point are many. You like to know the wind velocity at that point, the acceleration at that point, stress at that point, and so many variables are there, and each one will have 3 components. It is a 3-dimensional problem, so we will have 3 components. So, the number of components of a variable and the number of variables are so many, therefore, the total number of components will be enormous. When solving that partial system partial differential equations, the system that comes out of it is not a system which is amenable for the direct methods. So, in such cases of complicated problems, we would like to choose the iterative methods for the solution of this system of equations. Every iterative method connects the current iterate to the previous iterate. So, if I write down a method like x k plus 1, this is equal to h x k plus c, then I would call this x k plus 1 as a current iterate, at k plus 1th step, and x k is the previous iterate. Now, the method connects the current iterate with the previous iterate, wherein this H is called the iteration matrix. And C is a column vector. Involving the right hand side, column vector involving the right hand side, B. So, we would like to derive an iterative method which would look like this. If the iterative method is converging, then in the limit as k tends to infinity, this will tend to x. Therefore, if it converges, then x k plus 1 or x k will tend to x, the exact solution. It will tend to the exact solution, which is x is equal to A inverse of B. The solution is x is A inverse B. Therefore, if it converges, then x k plus 1 would converge to this particular value, the exact solution x is equal to A inverse B. Now, we were going to study in our next lecture, also later lectures, as to the properties of this matrix H, because this iteration matrix is the most important matrix. Now, the convergence or divergence depends entirely on the behavior of this particular matrix. It is possible that even a 2 by 2 system may diverge if you do not write it properly. We will give an example next time, that even if you take a 2 by 2 system and try to solve by an iterative method, it may diverge. Therefore, the properties of this iteration matrix is very important. When we have solved in the direct methods, we have solved it in the given form, Gauss elimination, and we also found when the pivot is 0, we had also used the partial pivoting, we have interchanged the equations and so on. Therefore, the order in which the iterative method is applied is very important. If you change the order, then the properties of the iteration matrix is going to change. That means, if you are interchanging first equation is 10th equation, then the property of this is H is going to change. Therefore, you may be making a convergent method as divergent method and a divergent method as a convergent method if you are using this particular type of interchanges. So, we shall do those things in next class.